So can you share your? We are
My computer is not the
no,
case.
yes, we can see it now, but it's
There's
okay.
quite a delay, so we'll see how well that works.
Yes.
See the slideshow mode now?
Yeah, we can see the slideshow. So
Okay,
David, when you want, please, thank you very much to be with us today. Thank you.
okay. Very much, Nuno. And hello, everybody. I hope you're all doing well under the difficult circumstance. I would like to thank Nuno for the kind invitation, and thank you for joining me today on this very interesting topic, of which I can only share a very brief overview. I also want to acknowledge several of my Keysight colleagues and also some of the eminent researchers who are true world experts in the field with whom I've had the pleasure of learning little tidbits. So here's how I plan to organize the talk. I'll start with some of the claims about the wonders of quantum computation, should they be realized. And you'll see what all the excitement is about. But I'll spend most of the talk talking about how microwaves and microwave engineering has the potential to this to become a reality. So we'll talk about qubits, the fundamental unit of quantum information, and give you a very little flavor about quantum algorithms and how they work. And then I'll try to summarize. And if the point of the joke is not quite evident, I hope it will be more clear at the end of the talk. Technology, of which quantum computing on the is a major part, has the potential to transform our society as profoundly as any technological revolution in our history, in my opinion. So in quantum mechanics has the ability, in principle, to guarantee secure and private communication. At the same time, paradoxically, the power of quantum communication enables, in principle, the of some of our classical security apparatus. So by factoring large numbers, we can potentially break some of the encryption protocols. And that, of course, is why so many of the governments in the world are spending so much money, as well as some of the opportunities to help humanity, such as simulate chemical, more accurately designed drugs, and sense things at exquisite sensitivities. So it's really quite impressive what some of the possibilities are. But why are we talking about this now? Well, you've seen about in many different ways. And here I'm just plotting the critical dimension of transistors as a function of time. And they're getting smaller exponentially. And already we're below 10 nanometers. And in 2 more orders of magnitude, we'll be down at the size of a single atom, a tenth of a nanometer or an angstrom. So a classical transistor can't work as a single atom. And all the hoops that the foundries have been going in to try to preserve Moore's law longer and longer will eventually have to come to an end when we're dealing with the classical parameter. So things like threshold voltages are getting harder to control as the number of atoms in the transistor basically decreased. So this is a fundamental paradigm change really being forced on us now. But the idea really that Feynman came up with in the mid-'80s was, well, why not stop fighting the inevitable and instead try to harness the wonderful and unique properties of quantum mechanics for computation. And that has really kind of wonderful scientific and technological breakthroughs that you're about to witness and have already. Historians of this area draw parallels between where we are now in quantum computation and where the semiconductor industry was somewhere in the 30s to 50s, when the fundamental came out of the academic labs, Bell Labs, and moved west and started Silicon Valley, for example. So it's an exciting time. So with that introduction, let me move on to some of the basics of qubits and look for some of these principles. And I will only be able to go through them very quickly and not as deeply as they should be treated. Classical bits, they can take a value of 0 or 1. And the quantum mechanical version of that is the qubit, quantum bit. And it's often said colloquially, a qubit can be in any state in between 0 and 1 inclusive. But a more precise statement would be that a qubit is an ideal two-level quantum mechanical system that can be in an arbitrary complex superposition of two basis states, which we call ket 0. So we can label these two orthogonal unit vectors in an abstract space, just like x hat and y hat are unit vectors in the plane. And the state, the most you can know about a qubit, this ideal two-level system, can be any superposition of those two. There's one constraint on the coefficients, which are complex numbers, namely the sum of the absolute squares is 1. And that constraint means we can parameterize these numbers in terms of the standard spherical angles. The state of a qubit then can be visualized as being any point on the surface of this sphere of radius 1. That's called the Bloch sphere. And we can associate at the north and south poles, respectively, the two different basis states, ket 0 and ket 1. So unlike a bit that can be one of two values, there is an infinite continuous set of quantum states that can be associated with the qubit. Now, an example of this ideal system, or for example, an electron, a free electron in a magnetic field. Photons, for example, let's take polarization. Let's say vertical and horizontal, you can think of those as the 0 and 1, for example, or right circularly polarized light and left circularly polarized light. For the electron in a magnetic field, it's spin up and spin down. So those are the two different basis states. Realistically, in systems now, we're talking about macroscopic objects like Josephson, et cetera. But we'll just use one example given the time. Now, we talked about the state of a qubit being any superposition. In addition to that, though, when you actually query a qubit, when you look at it or when you measure it, you get only one of two possible outcomes. So no matter what beta are, assuming they're both not 0 or one isn't 0, you can get this state, ket 0 or 1. You can get, for example, linear polarizers, you get either vertical or horizontal, for example, or circularly polarized right or left. Nothing in between. So that's very important because you can only retrieve then one classical bit of information when you measure a qubit, despite the fact that these coefficients can be anything and there can be infinite precision to them, therefore infinite information. You can only retrieve one classical bit. So that's not very useful. And when you measure the qubit, you get then the collapsing to either 0 or 1, depending on what you get. And that's called the collapse of the wave function. Now, there's a little bit more to the state and its relationship to these measurements. It turns out that the absolute square of these coefficients will actually give you the probability of getting the result that you found. Now, from a single, you cannot tell what these coefficients are. You have to repeat the experiment over and over and over again and make a measurement each time and then build up the statistics to get the values of at least the magnitude of alpha and beta. And that's because probability is fundamental to quantum mechanics. It has nothing to do with lack of information about initial conditions. It is an inherent property of nature. So philosophically, people used to say, well, the scientific actually on the fact that if you set up an experiment the same way and repeat it, you have to get the same answer. That is absolutely not true. You can define or prepare a qubit in exactly the same state, make a measurement and get a different result. All you can predict are the probabilities. Now let's make our way towards a real qubit. And we're going to start with the familiar LC linear electrical oscillator with an inductor and a capacitor. We can write the energy of this circuit in terms of the charge stored in the capacitor and the flux through the inductor this way. And as a function of charge flux, we call that the Hamiltonian. That's an exact mathematical analogy with a particle subject to a parabolic potential or linear restoring force, mass spring system from mechanics. And we know that the classical energy in terms of the momentum and the coordinates, we replace the momentum of classical physics with minus h bar d by dx, a differential operator, and Schrodinger equation. The Schrodinger equation is a value equation, just like many of those equations that we know from engineering. And it has solutions at discrete energy levels labeled by the integer n. And here is Planck's constant. And that's how we get the allowed energy in quantum mechanics. And so unlike a cloud particle in a parabolic potential, here's the parabolic potential, the classical particle can have any energy depending on its initial position and momentum, for example. But in quantum mechanics, the solution of Schrodinger's eigenvalue equation says there are only discrete energy levels allowed. And in this case, they are equally spaced by an energy of h bar omega, where omega, not too surprisingly, is the frequency of the LC oscillator, 1 over LC, as is familiar. But this is not yet a qubit. Remember, I said a qubit is an ideal two-level system, infinite number of levels. So we have to do something else. So what we do is replace the fixed inductor value with a nonlinear inductor. And fortunately, there is a nonlinear inductor that's also dissipationless, that's critical, in the Josephson junction. And a Josephson junction is just a sandwich of some kind of insulator by two superconducting pieces of metal, and then Cooper pairs tunnel back and forth. And it behaves as a nonlinear oscillator. That's all I'm going to say about the physics there. But because it's nonlinear, the energy is no longer exactly quadratic in the flux or the phase. As to next order, a quartic term, and there are other higher order terms that detract from the parabola of the potential energy. So instead of the dashed parabola, we get a curve that flattens out. And that changes the solution of Schrödinger's equation because it's a different system and produces the discrete but anharmonic LC oscillator spectrum. And because we can tune our microwaves to this transition, one of the key enabling relationships of microwaves to these systems, we can our attention to these lower two levels, and that gives us a good approximation to an ideal qubit. Now, quantum mechanics to the operation of this computational paradigm, and in order to preserve the discrete quantum nature of this system, we have to make sure that the thermal energy of the environment does not incoherently mix these levels. We have to be able to coherently manipulate transitions between the two levels of qubits in order to do anything useful. And to see how cold we actually have to make these, we first notice that the energy difference typically in these superconducting qubits typically in the 10 gigahertz range, or anywhere from 1 to 10 typically. And in terms of the frequency, which we can get by dividing, or in terms of the energy, we multiply by h bar. And there's an effective temperature, which we can calculate given Boltzmann's constant. And we see that corresponding to the transition frequency of 10 gigahertz microwaves is half a degree Kelvin. So it's very cold. And if we want this temperature energy to be small compared to the energy difference of the quantum states, we actually have to operate in the 1 to 10 to 20 millikelvin range. Now, for cold, it's much colder than outer space. Remember, there's a 3-degree background microwave radiation signature in space, and the orders of magnitude colder. So that's one of the many challenges. So try to sprinkle comments about the challenges. Keeping things really cold and making systems work at these frigid temperatures is a big challenge. Now, it's not enough just to have these levels. We have to be able to initialize them. We have to be able to coherently go from one level to, and therefore we make these qubits microwave circuits. So this looks just like a microwave circuit. Here's a resonator, here's a readout line, there are capacitors here, and the circuit is actually shown blown up here. It's very small, and there's a loop in a superconducting quantum interference device to enable a tuning of these levels by changing the magnetic flux through the superconducting device. And couple through lines to the resonator. We'll talk about that a little bit more. And then provide microwave pulses, which will manipulate the states of the qubit. So again, it's not enough to have levels. We have to be able to set the qubit into one of these initial condition, coherently manipulate with microwaves, which are then sent in here from a source, and then be able to measure the qubits, which we'll see we can do that by querying the resonator, which is coupled to the quantum mechanical device here. It's also therefore clear from the diagram and from what I've just mentioned that microwave engineering is really incredibly useful. The physicists are kind of begging us to help them with design and applying some of the knowledge of our society to help them engineer and produce and design these chips. Zooming out from that previous picture is this pretty picture from UCSB, the Martinez group. Here are 5 of those qubits called transmons or exmons for obvious reasons. Here are the resonators. Each resonator is attached to one of the qubits in these cases. Sometimes you can multiplex them. These lines provide the microwave control to manipulate the quantum state on the Bloch sphere, as well as tuning of the energy level difference. And again, you can recognize the microwave characteristics of these quantum chips. What's potentially different is that the chip has to live at these very, very cold temperatures at the bottom of what's called a dilution refrigerator. It's a cryostat shielded in this encasement. It often is a huge cylindrical device hanging from the ceiling above the lab. And you see all these microwave cables. They're typically 3 cables per qubit. So it's a tangled mess of equipment. And also there are filters and circulators and parametric amplifiers and all kinds of microwave equipment at different stages here. And there's 77 Kelvin here, sometimes 4 Kelvin in the middle, and down here, the millikelvin temperature. So there are all kinds of challenges. And scalability, trying to get many, many qubits, as we'll see, which are needed to do useful computations, makes this kind of connectivity very difficult. So one of the big challenges in the field is how can this system be scaled to hundreds or thousands or millions of fully functioning qubits? So I want to now show a little video, if it works, about microwave signals using a source and a mixer to actually the quantum state on the Bloch sphere. So we're going to be starting, say, in this case, let's say the ground state of this 2-level system. And depending on the phase, or the, say, whether it's an I or in the Q channel, and the amp pulse, we will be performing rotations from one point on the surface of the Bloch sphere to another. That's how we manipulate the quantum state. And I hope it will work. So we're now doing a rotation all the way to the bottom, Ket 1, changing the phase, going back to the ground state, now rotating around the y-axis, and now rotating halfway back. So we're at the equator, rotating another halfway back around the y-axis to the top. So by changing the amplitude and the phase of our microwave signals applied at the resonance frequency of the qubit, that's key, we can manipulate the quantum state determinist from wherever we started from to wherever we want it to go. Of where we want it to go depend on the algorithm. It's important to know that yes, system, it's probabilistic, but the Schrodinger equation is a linear differential equation. And if you don't measure, if you close your eyes and don't look, you can control the state of the qubit because the Schrodinger equation evolves deterministically. All right, I'm not going to show it again. Oops. All right. So here's a simple circuit, quantum circuit diagram. Very briefly to review what we just saw in the movie. We start the qubit in state, and we apply a microwave pulse. The first blue pulse, say in the I channel, flip into its excited state, and that was equivalent to a rotation around the x-axis by pi pulse. And then if you apply, you're back up to the other state. So you're effectively interchanging the two states, and you can represent that operation as this simple matrix, which is the Pauli X gate. And this is the logical representation of the NOT gate in quantum mechanics, where the operator operates on any vector in the two-dimensional column. So that's the NOT gate. But there's also operators, say the square root of NOT, which is the pi over 2 rotation, the rotation that gets you to the equator. And on the equator of the Bloch sphere, you get an equal superposition of the two basis states. And that's the prelude to doing all the computation. Also, it's very important that when you trigger another pulse, it's coherent, you know, with respect to the intrinsic clock of the qubit. It turns out that the relative phase of any state of the qubit is changing at the rate, at the frequency of the transition itself. So the precise phase when this same pulse is triggered again will determine whether you're applying a rotation around X, Y, or some other axis. That is also why microwave sources, we have to make sure that they're pure as much as possible, because phase noise will cause a jitter in the phase here, and we won't rotate the way we want to rotate, and we will get errors. And errors are bad for computing. Now, if we imagine applying a pulse at resonance for different lengths of time, but for each time, starting with a small time from the initialization of the state at 0, we then make a measurement, and we can get 0 or 1. As long as we're not right at 0, we can get 0 or 1. We don't know, but there's a probability that we'll get 0 or 1, and by making many measurements, we'll get a red dot here. So if the time or the duration of this pulse before we make the measurement is short, we've started out close to here, the angle, since we in the parameterization is close to 0, the probability of getting a 1 is very small, so we're always close to 0. But as we make a measurement for longer times, when this pulse is applied, say green, there's a larger and larger chance that when we make a measurement of this, but again, we have each point here is an average of thousands of measurements. If you actually were to make measurements here, you'd get, say, half the time 0 and 1. And if we continue the pulse at the resonance frequency of the transition, we will trace out ideally this oscillation in probability of getting a 1 or a 0 over time. And those are called Rabi oscillations. Now that's the ideal case. If the qubit were perfect, in reality, unfortunately, the superposition decays or decoheres. That's another big problem with real qubits. They don't last forever. In fact, they typically last on the order of, these days, maybe 100 or 200 microseconds. That's really good. So the key challenge is to make sure that your qubit lives long enough such that with microwaves you can perform the kinds of operations you want and enough of them to computation. So lifetimes are important for qubits, but just as important as their lifetime, it's how fast can you actually manipulate the states with your control signal. That's even more important. Okay, so where does the power of quantum computation come? I've shown you the basics of qubits, how they're manipulated, but why is it so much more powerful? Well, that's kind of a deep and hard question, but here is one of the. We talked about a single qubit is a superposition of the two basis states. If we have two qubits, the state of a 2-qubit system is a superposition in 4 dimensions. Each dimension or each axis can be labeled by the states of the individual qubits. And for 3 qubits, it's an 8-dimensional space, and by induction, the dimension is 2 to the n. So the space of a quantum state of n qubits scales exponentially with the number of individual qubits. That's completely different from a classical system. Classical system, you have the position or momentum of each particle. You add another particle, you just add the position and momentum of the next particle, and that defines the state of the composite. So for example, just to make it clear how dramatically different that is, it's estimated that there are 10 to the 80th particles in the known universe. Well, in terms of number of qubits, you solve this equation. It says that there are more states available to a system of n qubits for 270 qubits than there are atoms in the universe. And that means, or as some people would say, if every atom in the universe were dedicated to classical computation, you could do as much with 270 quantum bits as a classical computer. Another way to talk about that is to say, if you have a computational state for n bits classically, you have one of 2 to the n states, just one. But a quantum state is an arbitrary superposition of all 2 to the n states. So you have that in dramatically large computational space at your disposal. Oh, I should mention also that this recent demonstration of so-called quantum supremacy was done with 53 bits, qubits that is, and actually 54. One of them didn't work. I should have mentioned when I showed you the cryostat that there was a problem with one of those cables. And the challenges of trying to repair such a device, meaning you have to open up the cryostat, pull it out, wait for it to warm up, find the problem, debugging all those cables, fixing it, putting it back in the cryostat was too much. So they basically just used 53 of the qubits. And that was an abstract, not very practical algorithm, but they were able to demonstrate a superior result with their quantum computer. Anyway, that's a story in its own right. All right, so we talked about the exponential scaling of the quantum space with qubit number. That's important in another respect, in particular, a property only of quantum systems called entanglement. So here is the general 2-qubit state. As we've seen, it's 4-dimensional. And here's a very simple example. So C1 is 1, or 1 over square root of 2, and so is C4. Now this state is a well-defined state of a 2-qubit system, and it is so-called entanglement, because if we measure this state, as we said, it has to collapse into one of the states. Now there are 4 basis states. So if we measure 1 qubit and we find 0, then we know we've collapsed the state into 0, 0. If, on the other hand, we measure either qubit in the 1 state, it means this state has collapsed upon measurement into the 1, 1 state. And if it's in the 1, 1 state, for example, we know its partner has to be in the 1 state as well. Likewise, if we had measured 0, we know its partner has to be in the 0 state. And so there are these super classical correlations in measurements, and we can predict the result of a measurement across the universe without even having to make it. So for example, if we can somehow entangle 2 qubits, qubit 1 and qubit 2, and we send one of the qubits off across the universe, and then we measure qubit 1, immediately and instantaneously, we here in our lab know with certainty what the measurement of qubit 2 would be or will be when measured by somebody on the other side of the universe. And that's Einstein's spooky action at a distance, non-locality, and it's fascinating and mind-bending. But it's more than just interesting. means it actually is a computational resource. Because remember, I told you only one classical bit of information is retrievable from a single qubit. It turns out that you can encode and retrieve 2 classical bits of information from a single qubit if it's part of an entangled pair. And with multiple qubits, the information can be distributed among them in this entangled form. Another interesting comment is, again, that unlike a classical system composed of 2 particles, where each particle, almost by definition, can be considered to have its own state, in quantum mechanics, here is a state of a 2-qubit system, but neither constituent qubit can be said to have its own quantum state. That's a feature of entanglement. That we know how to manipulate our qubits. We know we need to entangle them. How do we query them in a practical sense? And I showed you the qubits and coupling to a resonator. Here's a schematic of that. What is typically done is a microwave signal is sent in from the equipment, going down through the layers of the cryostat, and you query the resonator, and you look for the resonance as a function of frequency. And it turns out that due to the quantum mechanical interaction of the qubit and the resonator, if you probe the resonator typically at, let's say, 1 gigahertz away from the resonant frequency of the qubit, so the qubit was maybe 10 gigahertz transition energy, the resonator designed to be, say, 11 gigahertz, the interaction between the qubit and the resonator quantum mechanically shifts the resonant frequency of the resonator. So by querying the resonator, you can infer what the state of the qubit was. And that's how you make a measurement of the qubit state. And effectively, what that means is that the state of the qubit is like a dielectric, and the dielectric changes as a function of the qubit state. So when you measure the readout resonator, you can infer through what the resonant frequency is, what the state of the qubit is. And again, this has to be done quickly before the qubit decohere. All right, so let's shift briefly into the algorithm. Slide from the MIT group. With a 3-qubit state to illustrate, there are 8 of them, but there are only 4 of them shown in the picture here. And by doing the pi over 2 pulses that we introduced earlier, we put individually qubits into a superposition state. Neglecting the normalization, a coherent superposition of all of, say, the 8 basis states as a starting point. And then the next step of an algorithm is to put the microwave pulses, or use different microwave pulses, say, for each qubit, where you change the coefficients of those states according to what your algorithm is. And then you let the probability amplitudes interfere. You close your eyes, you apply the pulses, and that will mix up through the time-dependent Schrodinger equation, the coefficients. Then you have to do these 2-qubit gates, which I didn't talk about, in order to entangle these qubits. That's important, but it's more complicated than I can go into. And then there's more quantum interference. And in the end, and this is the genius behind some of these algorithms, that you try to encode the solution into a particular but unknown basis vector. And if you write interference experiment, if you engender the interference such that in the end, one of the coefficients is approximately 1 and the other coefficients therefore are close to 0, sum of the square of the coefficients has to be 1. And then you make a measurement. The overwhelming probability of getting the right answer happens when this coefficient is close to 1. And then you make the measurement, that particular sequence bits that you retrieve is the answer. Fortunately, I can't give you a demonstration in the time for that, but it's marvelous and it really is genius. So a typical hallmark of quantum algorithms is that they're probabilistic. So with a high degree of probability, you'll get the right answer. It's very easy to check. But unlike what I've read, it's absolutely not true that all quantum algorithms are probabilistic. There are some quantum algorithms that are, in fact, completely deterministic. You will always get a definite answer. In the end, a quantum algorithm is really nothing but a set of microwave pulses. So we have multiple qubits here. Each one has a line. This is a quantum circuit diagram. The little boxes on one line are the microwave pulses, basically, that do certain things. The X gate we talked about, it's that pi pulse. These other gates manipulate states in slightly different ways. Any line or box connecting two or more qubits is a two or multi-particle gate that creates some kind of entanglement. Entanglement requires an interaction between two qubits or among multiple qubits. And to execute an algorithm, these pulses, as we mentioned before, have to be very carefully sequenced. Highly coherent multi-channel signaling is required. And you have to make enough of these predefined, or they don't even have to be fully predefined, but sequenced coherent pulses across multiple channels to execute the algorithms in a quantum computation. And so again, the challenges are the qubits can decohere. You have to make sure you do enough operations to be useful while they still are working. The temperatures are very cold, and there's still high error rates. Now there are, I guess we'll get to that, about how to correct errors, at least in principle. But it's nothing like 10 to the minus 14 or 16 error rates in a classical computer. They're down in 10 to the minus 4 these days. And finally, there's the big challenge of error correction. So given those error rates, you need a high degree of redundancy to protect against errors. And there are all kinds of errors. There's error in readout, there's error in initialization. If the microwave pulses aren't precisely at the right frequency or triggered at the right point in time or fully coherent, or the source has phase noise on it, you will be rotating, for example, the quantum states to places you didn't intend to, and those errors will add up. And so typically what we do in all cases, classical and quantum, is we use redundancy to protect against errors. So for example, we can use 3 qubits, which can be different states, but we look at a subset where, say, they're all 0 and all 1, and encode that lot 3 qubits using an obvious mapping. And then if we can query a quantum state and we find a state like this, know there was an error, and we can correct it. So we can correct this state to 111, for example, and this state to 0. And without going through the details, it's possible using entanglement with some extra qubits and measuring only the extra qubits, the ancillas as they're called, we can locate and define and locate which qubit had an error without querying it. Because remember, if we query the qubit, we destroy the information that was that it contained. We collapse the wave function. But by collapsing only the part of the entanglement between extra qubits and the data qubits, we can infer the parity basically and know which qubit had an error and then trigger one of those other microwave pulses, an X gate or a Y gate that rotates around Y, for example, and correct the error without looking at the qubit itself. So that's very roughly how error correction works. But because the error rates are large, we need to trigger waveforms depending on our measurements. The measurements have to be made quickly. Pulses have to be sent out quickly, coherently to the channel that has the qubit that had the error. So a lot of real-time decision-making and fast feedback is important. And typically now, the redundancy between the physical qubits that we need for a good logical qubit is on the order of 1,000. So clearly that's not practical yet. But so that's one of the big enduring challenges that the people pursuing practical quantum computation need to overcome. But so that kind of summarizes the talk. And I do want to emphasize that I hope it's clear that microwaves are really the sweet spot of the quantum modality. So we talked about superconducting qubits, but there are spins also that work at those kind of microwave frequencies, also very cold. There are others that are optical, like trapped ions, etc. Waves are really the predominant control mechanism for the most practical systems so far, with the possible exception of photons. Microwaves and microwave engineering, designing the chips, which are microwave chips, with good cavities, which we didn't really talk about, simulation, classical electromagnetic simulation, planar microwave analysis are key to designing qubit chips that are practical. And then fast feedback, highly coherent multi-channel systems of microwave control is a real key aspect to making successful commercial and practical enterprise. Milestones like the quantum advantage demonstration continue to be made. Significant progress is happening. Dramatic increase in funding over the last many years. And within the IEEE and other communities, there's an explosion of this new field called quantum engineering. It's interdisciplinary. There's mathematics, computer science, physics, microwave engineering, and a fascinating, interesting time to be working in this field. I want to thank you for your attention. Remind people that the IEEE is heavily involved. There is a quantum conference. Here's the URL. This is scheduled to occur in October. And I encourage you to explore this, the other involvement of IEEE in this fascinating field. So with that, I'd like to thank you for your attention. I'll do my best to answer questions if there are any, or you can always email me and I will endeavor to get back to you. So thanks again.
Okay, David, thank you very much for this interesting talk. It was very, very interesting, and hopefully, I think it will be motivated also for new people to join this area of quantum computing. And I will now open the session for questions. So if you have any, you can either your microphone or you can put the questions in the question and answer or chat, whatever you prefer.
Hello, can you hear me?
Yes, we can hear you.
Yeah, my name is Sai. I have a question for Dr. David Root. Actually, a question and a comment. The question was the equation you showed for the quantum states. Is that a direct ket vector equation?
Let's see.
The
Is
two
this the one?
states that you showed,
So
you know,
this one?
the 0 and 1. Is that a ket vector?
Yes. So psi is a ket vector. And typically,
right.
Yes.
Okay, so now the classical form, like a Hamiltonian type of equation, will not work, I guess.
The Hamiltonian, what's so nice about quantum mechanics is, well, like classical mechanics, there's Newton's law, so you can derive classical equations of motion using Newton's law or electromagnetics, but you can use Hamilton's equations to get the classical equations, and you can use Lagrange's equations. Quantum mechanics can be quantum mechanics solutions by the Schrodinger equation or Lagrangian inversion. So it actually goes over. Yes. So the Hamiltonian is the same, basically, but there's a between the classical dynamical variables and the quantum mechanical operators that represent dynamical variables in quantum mechanics. But yeah, the Hamiltonian formulation works fine.
Okay, and the other question on that was that in quantum mechanics, in theory at least, you can have non-degenerate states of particles. Would that help in being able to make this qubit system more measurable or more efficient if we can get only non-degenerate states of any particle system?
Actually, yes, it's the fact that these two states are non-degenerate. So a degenerate state would be multiple states of the same energy. So almost by definition, a qubit is a with different energy. Now, you don't have to have different energies. So for example, if you have photons as your qubit, you can have the two states being different polarizations.
Right, like
so in that case,
the spin quanta could be two states of an electron.
Well, an electron is a spin a half. So its angular momentum or its spin angular momentum can have only two values, say up or down. So a two-state system, very ideal an electron in a magnetic field. You can add a photon, not just polarization. It turns out you can make a qubit out of photons of different energies. So there are all kinds of wonderful things you can do. Some are degenerate, like a photon of the same energy with different polarization. Most of the time, most of the systems are non-degenerate approximately two-level systems that have different energies.
Right. And I have one comment. I have done some work with another company in supplying some microwave products for quantum computing. And the difficulty is that so far, the semiconductors that work at cryo states are, especially for oscillator or amplifier, are rather very limited, and that makes designing microwave components for quantum computing a lot more difficult, especially for low noise type applications.
That's a very good point. There's a huge opportunity to improve the electronics for quantum, and probably is done, say in Europe at the Technical University of Delft, using cryogenic CMOS devices. that can work down at 4 Kelvin and maybe slightly lower.
Right.
So even though the quantum processor has to work at millikelvin,
Exactly.
the electronics can be sort of placed lower in the crop. So that's an important trend. In terms of other microwave components, HEMTs are used to for amplification, not at the millikelvin level certainly, or even the 4 Kelvin, but low noise amplification is critical. There are Josephson junction-based traveling wave amplifiers, nearly quantum limited amplifiers that are necessary. I didn't show you the details of some of the plumbing with amplifiers. Circulators are needed. So there's a huge opportunity for contributions for some of these critical components to make the electronics work. So that's a very important comment. Thank you for making it.
Okay, thank you very much for
Thank
your
you very
question.
much.
I have a question in the chat. So someone is asking if you have to recommend a book for beginners on quantum computing, if you have
Yes.
any suggestion.
Yes, I do, and I didn't have the time to go into that. I can, if you, I can send you a list with the detailed, but I want to emphasize that microwave engineers who know just the tiny bit of linear algebra, which you do for matrices, it's quite possible to learn this stuff fundamentally based on a standard microwave engineer's background, I think. So, I mean, off the top of my head, there's a book by Leonard Susskind. Actually, let me pull it from my shelf here. It's called Quantum Mechanics, the Theoretical Minimum by Susskind, Susskind. It has one of the most lucid, correct, but elementary treatments of qubits, basically. It's very, very readable. And I guess I would start with that. But please send me an email and I'll provide you a list, because I've developed internal classes for Keysight and recommend that book along with others. There's a great deal of educational work being considered by the IEEE as well as many of the other agencies, because it's clear that there's a need to educate the workforce. Physicists need to understand more microwave engineering, but microwave engineers need to understand more of the physics. And I find that personally quite interesting. And it's exciting, and I think most microwave engineers have the tools to pick this up.
Okay, thank you very much. So
Sure.
we have time for one more question. There is anyone else? If not, thank you very much, David, again for this amazing talk. And we'll continue our chapter share meeting at this stage. Thank you very much, David.
Thank you all.
Thank
My
you.
pleasure.
So, as I said, we will continue our chapter share meeting at this stage by presenting a group of activities that our chapter shares around the world has been doing